Hi, I'm Anna Newman, and this is my digital logic project for the 5-switch enumerator. I will be using a D0 board where the first 3 LED lights will count in binary how many of the last 5 switches are switched on. The decimal number will also appear. Part 1 is a 2-level approach which creates a sum of products expression where each switch is a different input. 3 different SOP expressions will be used to create a binary number for however many switches are on. F0 represents the least significant bit, which will light up the LED farthest to the right, and F2 will represent the most significant bit, which will light up the third LED from the right. I will be making 3 different Carnot maps. The SOP expression for the F2 will represent when there are 4 or 5 switches turned on, which is what I've highlighted in the picture shown. Here is a 5-variable Carnot map. A 1 represents when a switch is turned on, and a 0 represents when a switch is turned off. Every time when the inputs add up to 4 or 5 ones, I will put a 1 in the box because that means there are 4 or 5 switches turned on. Each one is an implicant, and I will group them by 2's to make essential prime implicants. Each essential prime implicant is a product of inputs, and all the products together will create a sum of products, which is what the expression is below. There are 6 gates and 25 inputs, which makes the cost of the expression 31. Here's a Carnot map of F1. There are 34 gates and 77 inputs, which makes the cost of 111. Here's a Carnot map of F0, which has 57 gates and 136 inputs, which makes a cost of 193. Here is my Verilog code, where each switch is designated to a unique X, and each LED light is designated to a unique output F. The SOP expressions I just discussed are assigned to the outputs, so when those expressions are true, a particular LED light will light up. This is a pin planner that assigns each output F to a pin on the D0 board. Here 2 switches are turned on, so the second LED light is lit up, which represents the binary number 2. Here 3 switches are turned on, and the 2 LED lights in binary count to 3. Part 2 splits the 5 switches into a set of 2 and a set of 3 switches, which will be added together to display the LED lights. Here is a truth table for the first and second switch, where G represents the binary number. G0 will be the SOP expression for when one of the 2 switches is on, and G1 will be the expression for when both switches are on. The other 3 switches are represented in H. H1 is the SOP expression for when 2 out of the 3 switches are on, or all 3 switches are on. H0 is the SOP expression for when there is one out of the 3 switches on, or all 3 switches are also on. Here is the Verilog code I wrote for part 2. I created a 3-bit array for G, H, and F. G of 0 and G of 1 are the SOP expressions for the first 2 switches, represented as the inputs X1 and X2. H0 and H1 are the SOP expressions for the 3 other switches, represented as X3, X4, and X5. Because a set of 2 and a set of 3 switches alone can't have 4 or 5 switches, H of 2 and G of 2 are equal to 0, but are still necessary to have. G and H are added together in binary to create F. F will display the LED lights in binary for however many of the 5 switches are turned on. F of 0 represents the least significant bit, and F of 2 is the most significant bit. Splitting the 5 switches into sets of 2 allows for smaller SOP expressions, which helps there to be less error and causes it to be less time-consuming. Part 3 is a high-level behavioral description where there are no SOP expressions. Here is my Verilog code for part 3. I use an always block so that my input variables, which are still the 5 x's, are able to constantly be changing. When x is 1, the switch is on. When x is 0, the switch is off. So if I add up all the 1's, then it tells me how many switches are on. So my output F is equal to all the X's added up, so that tells me how many switches are on. F of 0 is still the least significant bit, and F of 2 is still the most significant bit. In this part, I made the D0 board show how many switches are turned on in decimal. Line 9, decoder calls another function to display the particular lights to show the decimal number. I pass through F, which is the binary number for how many switches are on, and display is a 7 output wire. This is the code to show the decimal display. Each case represents a different number to be shown on the D0 board. The zeros and ones assigned to num tell the hexes whether to light up or not. With certain ones lit, a decimal number is shown. This is the pin planner that assigns each display and F output to a pin on the D0 board. So this is me playing with the D0 board. You can see the LED lights changing in binary and the decimal number changing as the switches move up and down. I wrote this code 3 different ways. I think the last way is probably the best way to be written for like time consuming and error wise. You just add them up all real quickly and it's there, unlike the other two where you had to have AND gates and OR gates. Yeah, so this would be the end of my video. Thanks for watching. Sorry I sounded like a 5-year-old robot. Yeah, not very good at being entertaining with this stuff, but I think it's cool. So, coolness points. Woo! Thanks for watching.